Hello students, in this video we will discuss very important topics, Poisson brackets and properties of Poisson brackets in classical mechanics for BSc part 3 physics honors course in lecture number 10 of classical mechanics. First of all, we have to define Poisson bracket. Poisson bracket is a special kind of relation between a pair of dynamical variables of holonomic system which remains invariant or unchanged in any canonical transformation. Poisson brackets two dynamical variables, that is a pair of dynamical variables. Dynamical variables are those variables which are related to motion. तो Poisson brackets टू डायनामिकल वेरिएबल्स के बीच एक स्पेशल टाइप का रिलेशन है किसी होलोनोमिक सिस्टम का जो किसी कैनोनिकल ट्रांसफॉर्मेशन एनी कैनोनिकल ट्रांसफॉर्मेशन के अंदर के अधीन इनवेरिएंट रहता है, दैट इज अनचेंज रहता है. सो द रिलेशन बिटवीन ए पेयर ऑफ डायनेमिकल वेरिएबल्स ऑफ होलोनोमिक सिस्टम which remains invariant under any canonical transformation are called Poisson brackets. Write down Poisson bracket is a special kind of relation between a pair of, that is two, a pair of dynamical variables Dynamical variables are those variables which are related to motion. Dynamical variables of a holonomic system. Holonomic system we have already discussed. Discussed in the earlier video of classical mechanics of a holonomic system which remains invariant. Invariant means unchanged. Which remains invariant under any canonical transformation. Now, use of Poisson brackets. What is the use of Poisson brackets? Poisson bracket is mainly used to construct new integrals of motion from the known ones. Poisson bracket is mainly used to construct new integrals of motion from the known ones. Poisson bracket का यूज होता है दिए गए इंटीग्रल्स ऑफ मोशन. अगर इंटीग्रल्स ऑफ मोशन पहले से मालूम है तो उनके हेल्प से न्यू इंटीग्रल्स ऑफ मोशन को कंस्ट्रक्ट करते हैं. राइट डाउन Poisson bracket is mainly used to construct new integrals of motion from new integrals of motion from the known ones, from the known ones. Poisson's bracket or Poisson's brackets are the classical analog of commutation relation between operators in quantum mechanics. Poisson brackets क्वांटम मैकेनिक्स में ऑपरेटर्स के बीच कम्यूटेशन रिलेशन का क्लासिकल एनालॉग है, दैट इज इन क्लासिकल मैकेनिक्स. क्वांटम मैकेनिक्स में ऑपरेटर्स के बीच कम्यूटेशन रिलेशन के एनालॉगस है क्लासिकल मैकेनिक्स में पॉइसन्स ब्रैकेट्स और पॉइसन ब्रैकेट्स. तो पॉइसन ब्रैकेट्स क्लासिकल एनालॉग है, दैट इज पॉइसन ब्रैकेट्स आर एनालॉगस टू कम्यूटेशन रिलेशन बिटवीन ऑपरेटर्स इन द क्वांटम मैकेनिक्स. So write down Poisson brackets are the classical analog of commutation relation of operators in quantum mechanics. Now we can mathematically define Poisson bracket of a pair of two dynamical variables, say capital X and capital Y, related to position coordinate q and momentum small p. So mathematically the Poisson bracket of a pair of two dynamical variables x and y can be expressed as xy under big bracket, which is the symbol of Poisson bracket, similar to the commutator bracket we used in quantum mechanics for operators. Thus, the symbol of Poisson bracket is big bracket, big square bracket, similar to commutator bracket used in quantum mechanics. So mathematically, the Poisson bracket of two dynamical variables or a pair of dynamical variables, two dynamical variables, x, say x and y. So the Poisson bracket of a pair of dynamical variables or a pair of means two dynamical variables, a pair of, that means two dynamical variables say capital X and another variable is capital Y. Say capital X and capital Y. Capital X and capital Y are two dynamical variables. So the Poisson bracket of a pair of two dynamical variables X and Y, capital X and Y, related to position, a small q, and momentum, a small p, can be expressed as under bracket, that is under the square bracket xy, which is the symbol of Poisson bracket, similar to commutator bracket in quantum mechanics. So two dynamical variables capital X, comma Y, under a square bracket, under big bracket, related to position coordinate q and momentum p, तो सफिक्स में q कॉमा देकर के p. So Poisson bracket of two dynamical variables capital X and capital Y is denoted by the symbol under the square bracket capital X comma capital Y, bracket closed, in suffix q, which is the position coordinate, comma p, which is momentum. So two dynamical variables X and Y are related to position coordinate q and momentum small p, and this can be written as del x upon del qi into del y upon del pi, del p, del small pi, minus del x upon del pi into del y upon del qi, and this is both terms are kept under the square bracket or big bracket. So Poisson bracket of a pair of two dynamical variables X and Y can be written as, can be expressed as under the square bracket capital X capital Y, bracket closed, both are the functions of position coordinate q and momentum p. So q comma p equals to del x upon del qi into del y upon del pi in the first term inside the square bracket, minus in the second term we have del x upon del pi. Qi is exchanged, qi position is exchanged by momentum, partial differentiation in the denominator, into del y upon del qi. That is now position, now momentum pi of the first term del y upon del pi, and in the second term pi is exchanged by qi. That is momentum is replaced by position in the second term. So Poisson bracket of a pair of two dynamical variables capital X and capital Y is mathematically defined as or mathematically expressed as under big bracket or a square bracket capital X capital Y, which are related to q and p, that is the function of position q, a small q, and momentum p, equals to under a square bracket, which is the symbol of Poisson bracket, under square bracket del x upon del qi into del y upon del pi in the first term, and second term of this bracket, Poisson bracket, is minus del x upon del pi in place of del qi into del y upon del qi in place of del pi. And suppose it is equation number 1. And this is the mathematical definition of or mathematical representation of Poisson brackets of two dynamical variables capital X and capital Y, which are the functions of position coordinate small q and momentum small p. That is, two dynamical variables X and Y are related to position q and momentum p, which are represented in suffix of this square bracket, which is the symbol of Poisson bracket. Now we have to discuss properties of Poisson brackets. First property of Poisson bracket is that the Poisson bracket does not obey commutative law of algebra. Write down the Poisson first property of Poisson bracket is number one. The Poisson bracket does not obey the commutative law of algebra. That is, for a pair of dynamical variables or for two dynamical variables X and Y, we can write under a square bracket, that is, which is the symbol of Poisson bracket. So under the square bracket, variables, two variables, capital X, comma, capital Y, bracket closed, not equals to Y, that is, not equals to under bracket, that is a square bracket, Y, comma, X. Thus it is clear that the Poisson bracket of two dynamical variables, say X, capital X and capital Y, does not obey the commutative law of algebra, because under bracket, under square bracket, capital X, comma Y, bracket closed, is not equals to under bracket variable Y, comma X. Or we can write under bracket, under square bracket, X, comma Y, bracket closed, equals to minus Y, under bracket, under square bracket, Y, comma X, bracket closed. Minus sign indicates that two variables X and Y, that is Poisson bracket of two variables, say X and Y, does not obey commutative law of algebra. Now second property is the Poisson bracket obeys distributive law of algebra. So write down the Poisson bracket obeys commutative law of algebra. That is, if we take dynamical variables capital X, capital Y and capital Z, that is three dynamical variables, then under a square bracket or under big bracket, which is the symbol of Poisson bracket, capital X, comma, now in second term y plus z equals to under a square bracket capital X comma y plus capital X under bracket under square bracket in the second term of RHS. First term is under a square bracket x comma y plus second term is x under a square bracket or under big bracket capital X comma z, which is similar to distributive law of algebra. And in the another form we have that is product of two dynamical variables in the second term in the square bracket, that is second term of the square bracket. A square bracket is the product of two variables, dynamical variables y and z in place of sum. इस केस में स्क्वायर ब्रैकेट के अंदर एलएचएस में टू डायमेंशनल वेरिएबल्स y एंड z का सम है, एडिशन है, लेकिन सेकेंड सिचुएशन में अब y एंड z का प्रोडक्ट लिया जाए तो उस सिचुएशन में भी डिस्ट्रीब्यूटिव लॉ ऑफ अलजेब्रा होल्ड करेगा पॉइसन ब्रैकेट ऑफ डायमेंशनल वेरिएबल्स, that is and under bracket x comma y into z equals to, now y can be taken out of the square bracket, so we have y under bracket x under square bracket capital X, which is a variable, comma z plus in the second term under bracket it can be written as x comma y bracket closed and out of the bracket it is z. फर्स्ट ब्रैकेट में y को बाहर कर लिया गया, y अंडर स्क्वायर ब्रैकेट x comma z, that is Poisson bracket of x z, plus now Poisson bracket of two variables x and y, so under bracket x comma y bracket closed, that is we have represented Poisson bracket of x and y by this square bracket or big bracket, that is square bracket capital X comma y. This is the Poisson bracket of two variables and two dynamical variables x and y, and outside the bracket it is z. Thus it is clear that Poisson bracket obeys commutative law of algebra. Now next property is that is fourth property. Fourth property is qi or position coordinate. We represent position coordinate by a small q and also by capital Q, and momentum as a small p and also capital P. We have already used in both notations for old coordinate system and the new coordinate system in canonical transformation. So commutation relation, Poisson bracket is similar to commutation relation of operators in quantum mechanics. So Poisson bracket of position coordinate q and momentum p, that is qi, Poisson bracket of qi and pi, Poisson bracket of qi and pj. Pj represents momentum, qi represents position. So Poisson bracket of position coordinate q and momentum qi, say qi, and momentum coordinate pj can be written as delta ij, where delta is the Kronecker delta, which we used in quantum mechanics, Kronecker delta. So now Poisson bracket of position coordinate qi, small qi, and momentum coordinate pj. So Poisson bracket of position qi and momentum pj can be expressed by the square bracket qi comma pj, and it is equal to delta ij, where delta is Kronecker delta. If I not equals to j, then delta ij equals to 0. If delta ij equals to 0, when I not equals to j, we have already used it in quantum mechanics. That is condition of normalization and orthogonality. So delta ij equals to 0. Fourth property is Poisson bracket of position coordinate qi and momentum pj, that is under square bracket qi comma pj equals to delta ij, where delta is Kronecker delta, and delta ij equals to 0 if I not equals to j, and delta ij equals to 1 if I equals to j. I is equal to j, then delta ij, Kronecker delta, value of Kronecker delta is equal to 1. So this is the fourth property of Poisson bracket. Next property of Poisson bracket is Poisson bracket of two momentum coordinate or two position coordinate. Only indices are different, that is pi and pj, and qi and qj. So Poisson bracket of ei and pj is equal to 0, and also Poisson bracket of two position coordinates, that is qi and qj, is also equal to 0. So this is property number 5. It is qi under the square bracket qi qj, that is Poisson bracket of two position coordinates qi and qj equals to 0, and also Poisson bracket of two momentum coordinates pi under the square bracket a small pi comma pj bracket closed is also equal to 0, and we can prove it by the mathematical representation of Poisson brackets, which we have already discussed in this video as equation number 1. So with the help of equation 1, that is mathematical representation of Poisson brackets of two dynamical variables, say x and y, we can prove this relation. That is under Poisson bracket of qi and qj, that is under the square bracket qi qj equals to 0, and under square bracket pi comma pj, that is Poisson bracket of momentum, two momentum coordinates, that is pi and pj, is also equal to 0. Now some more important properties of Poisson brackets we have to discuss. So property number 6, which is the time derivative, partial time derivative of Poisson bracket of two variables. Now say two variables are u and v. So partial time derivative of two dynamical variables, say u and v in place of capital X and capital Y. अब कैपिटल एक्स एंड कैपिटल वाई जो अर्लियर हमने पहले टू डायनेमिकल वेरिएबल्स को यूज किया था, उसके जगह पर अब यदि टू डायनेमिकल वेरिएबल्स यू एंड वी का यूज किया जाए, स्मॉल यू एंड स्मॉल वी का, तो उसका अगर टाइम डेरिवेटिव लिया जाए पार्शियल टाइम डेरिवेटिव, तो उसे भी हम एक प्रॉपर्टी के रूप में एक्सप्रेस कर सकते हैं. तो सो नाउ प्रॉपर्टी नंबर 6, and it is partial time derivative del upon del t of the commutation relation of two dynamical variables, say u in place of x and v in place of y. अब x के जब बदले में डायनामिकल वेरिएबल u का यूज किया गया एंड सेकेंड डायनामिकल वेरिएबल y के जगह v का यूज किया गया. नाउ द टाइम डेरिवेटिव, पार्शियल टाइम डेरिवेटिव ऑफ Poisson bracket of two dynamical variables u and v, that is del upon del t under square bracket u comma v bracket closed, can be written as, can be expressed as del u upon del t, keeping second variable v constant. So so under square bracket, first term is in first term of parenthesis under the square bracket or under the big bracket, del u upon del t, del upon del t of under square bracket u and v equals to under bracket del u upon del t, keeping v constant, so comma v, plus now in second term it is u, that is first variable now remains constant, u first variable, taking first variable u as constant in the second square bracket. So it is under square bracket u, which remains constant, taking u as constant, comma del v upon del t, that is time derivative, partial time derivative of the another variable, another dynamical variable v, that is del v upon del t. So we have partial derivative of two variables, two dynamical variables, say u and v, that is del upon del t under square bracket u comma v equals to under square bracket del u upon del t, that is time derivative of the first variable, partial time derivative of the first variable u, del u upon del t comma v, bracket closed, square bracket is closed, plus under square bracket u, that is first variable, taking first variable u in the second square bracket as constant, so u square under square bracket u comma del v upon del t, that is time derivative of the second variable, del v upon del t. And this is the sixth property of Poisson brackets. Now one more important, very important property which we will discuss in the separate video, that is Jacobi identity. The proof of Jacobi identity we will discuss in a separate video. So number 7 property is a very important property which is called Jacobi identity. If you take three dynamical variables u, v and w, so we can write number 7 property of Poisson bracket is Jacobi identity, which is Jacobi identity is under bracket u, under square bracket u, under bracket, under first term is u, under the big bracket, the square bracket. Now under bracket we take another bracket v, it is not a square bracket, simple bracket, v comma w, a square bracket is closed, so it is u under square bracket u comma v under bracket v comma w, plus under the square bracket now it is v comma a square bracket, now inside the simple bracket it is w, other two variables w and u, a square bracket closed, plus in the third term We have now W comma अंडर ब्रैकेट Q कॉमा V ब्रैकेट के अंदर Q1 V को एक साथ रखा गया एंड W को फर्स्ट टर्म में इस B ब्रैकेट के अंदर में, दैट इज Poisson ब्रैकेट ऑफ वेरिएबल W एंड Q1 V, that is Q1 V are together inside a bracket, and sum of all three terms will be equal to 0. We can prove it, Jacobi identity we can prove it, that is sum of all three terms in LHS, that is under bracket, under square bracket U, comma, under bracket V, comma W, plus under square bracket V, comma, under the small bracket W, comma U, W और U एक साथ है सेकेंड टर्म में, ब्रैकेट क्लोज, स्क्वायर ब्रैकेट क्लोज, प्लस अंडर स्क्वायर ब्रैकेट W, comma, under small bracket U, comma V, square bracket is closed, is equal to 0, is equal to 0. The sum of that is the sum of all three terms is equal to 0, and it is called Jacobi identity. Jacobi identity, which we have to prove Jacobi identity, but in the another video. Now one more, that is the last important property which we are going to discuss, is property number 8. Property number 8, and that property is Poisson bracket of two dynamical variables is invariant under infinitesimal canonical transformation. Poisson bracket of two dynamical variables is invariant, that is unchanged, that is invariant means unchanged under infinitesimal canonical transformation. This is also a very important property. So property number 8 of Poisson bracket is, which is the last property of this video also. There are various properties of Poisson bracket. Out of those properties, these are very important properties we have discussed in this video. So Poisson, write down Poisson bracket of two dynamical variables suppose two variables phi and psi, or u or v, or x and y, u and v, we can take u and v to dynamical variables x and y, or phi and psi. So Poisson bracket of two dynamical variables is invariant, that is unchanged, invariant under infinitesimal canonical transformation. Under infinitesimal means very small, infinitesimal canonical transformation. This is one of the important properties of Poisson bracket, and here we have where it is property number 8 in this video. So Poisson bracket of two dynamical variables is invariant under infinitesimal canonical transformation. Which we can also prove it similar to Jacobi identity, but we will prove these two properties, that is Jacobi identity particularly, and we can also prove property number 8 of this video, that is Poisson bracket of two dynamical variables is invariant under infinitesimal canonical transportation. So both properties can be proved by using the mathematical form of Poisson bracket of two dynamical variables. Now this video is completed. Thanks all of you for watching my YouTube channel.